Welcome to this video session. My name is Samuel Dominic Chukwu Emeka, aka Sam Dom for Peace. In this video session, we shall discuss linear homogeneous recurrence relations. This will be part one of the video. So let me just write in part one. Part one. So in this video we shall write explicit formulas of linear homogeneous recurrence relations. So with recurrence relation, when you say that when you have a recurrence relation, it is actually a recursive sequence. Okay, is a recursive sequence whereby you're given initial conditions, and then you get each term is God from the preceding term or terms. Okay, with recurrence relation, you get each term from preceding terms or preceding term, whichever way it goes. However, with explicit formula is a formula that allows you to compute any term of the sequence. Okay, you can, if you want to compute the fifth term of the sequence, you can compute that. If you want to compute the 10th term of the sequence, you can easily compute that. You don't need to compute the 10th term from the 9th term. Okay, when you have recurrence relation, for you to get the 10th term, you might need the 9th term or the 9th and the 8th term. Each time you get it from preceding term or preceding terms, depending on the relation, on the formula for the relation. Okay, a recurrence relation is recursive. It's a recursive sequence. Each time you get it from the preceding terms or the preceding term. Okay, but the explicit formula is whereby we are just given the sequence, the nth term of the sequence. Okay, we are given the nth term of the sequence right away. We can compute the 10th term right away without having to know the 9th term or the 9th and the 8th term. Okay, so it is, before you continue with this video, it is important that you have a good knowledge of sequences. And when you have the good knowledge of sequences, you also have a knowledge of explicit formula of a sequence, the nth term of a sequence, arithmetic sequence, geometric sequence, the nth term of a series. Okay, so AP, GP, or AP progression, AP arithmetic sequence, some textbooks call it arithmetic progression, geometric progression, series in general. It is good you have a good understanding of that. Then you also need to have an understanding of recurrence relation. So you can view the previous videos we did on sequences before you continue with this. Okay, it's very important. All right. We say that a linear homogeneous recurrence relation is a relation of the form, okay, it is a recurrence relation of the form. You have that the nth term, let's say A subscript n, the nth term of the recursion, okay, recursion or recurrence. Okay, a recurrence relation is a recursive sequence. The n term is equal to C times a n minus 1 times the previous term plus d times a subscript n minus 2 previous terms, okay, plus e times a subscript n minus 3, okay, plus f times a subscript n minus 4, and then plus, it goes on and on. You put your ellipses, 3 dots, plus, we can say G or M, or P. P, let me say P. P times A N minus K. Okay, so let's observe this. And I don't want you to, to be stressed out on all these terms. The main thing is to understand the concept. The main thing is to understand the concept. So let's look at this now. This here, the nth term, okay? A subscript n is the nth term of the linear recurrence, okay? Linear recurrence relation. The nth term is C times the previous term plus D times the term before the previous term and the rest of them. So our C, D, E, F, P, okay, because we can have it up to P. For the constants, these are constants that multiply those terms, okay? They are what we know as the constants that multiply those terms, okay? And then you can notice here, this n minus 1, previous term, n minus 2, the term before the previous term, n minus 3, the term before the previous term, okay, up to n minus k. K is the degree, okay? So we can say linear homogeneous recurrence relation of degree k, So it kind of tells you, when you look at the last term, it tells you what degree would it be. Okay, what degree is it going to be? That is what it tells you. Let's look at some, and of course you know that this n minus 1 is the previous term before the nth term. Okay, n minus 2 is the previous term before the previous term before the nth term. You understand what I'm saying? A subscript n minus 1, okay, is the previous term, is the term before the nth term, okay? The term before the nth term, okay? Then the term before the term, n minus 2, the term before the nth term, and the rest of them. Previous term before the nth term, okay? Then A subscript n minus 2 is the previous term, or you can say just the term before, okay? If you say the term before, that is similar to saying previous term. So let me just say term before the nth term. Let me just write it that way. So it will not be like tautology. Term before the nth term. Before the nth term. And then this will be term before the term before the nth term. So term before the nth term. And that is the way it goes, okay? That's just the way it goes. It's recursion. It's recursive sequence. It's recursive sequence. Now, let's kind of look at this for a moment. If we have something like this, if we have something like a to the n equal to 7 times a subscript n minus 1. If you just have just this. Okay? This, I'm going to use a yellow chalk. This is degree 1. Degree 1. Okay? Because the last one is what you have. This is a linear homogeneous recurrence relation, degree 1. Linear homogeneous recurrence relation, degree 1. If you have it this way, a subscript n, the nth term, to be maybe 7a subscript n minus 1 minus 3a subscript n minus 2. Okay? This is degree 2. This is degree 2. Degree 2. Remember, this is degree k, is the last one. And this last one, n minus 2. That means it's degree 2. If you have a subscript n to be 7a subscript n minus 1 minus 3a subscript n minus 2 minus a subscript n minus 3. Okay? This is degree 3. This is degree 3. And so on and so forth. And so on and so forth. Okay. Now, in this video, we are going to be concerned with degree 2. Our interest is degree 2. That is our interest, degree 2. That is what we are concerned about. And we want to write, we are given a recursion, we are given a recurrence relation or a recursive sequence. If I say recurrence relation, recursive sequence, they mean the same thing. So we are given a linear homogeneous recurrence relation of degree 2. And we are going to write the explicit formula of that. We will write the explicit formula of that and we will check it. The nice thing about this is after you write the explicit formula for that, because like I said, with the explicit formula, it's a formula that allows you to calculate any term of that sequence, any term at all. Right now, this is not explicit formula. For us to get the second term, we need the first term. Without the first term, we cannot get the second term. It's recursion. For us to get the third term, for this one, we need the first term and the second term. You see that? Without the first term and the second term, for this, we cannot get the third term. That is the one of degree 2. However, what we are going to do is, we are giving a recurrence relation, degree 2. For this video, we are just interested in degree 2. And we will now write the explicit formula for that relation. And we will check to see whether it works. We'll check it to see whether it works. We'll write the explicit formula and we'll just check to see whether it works. Okay? So, for us to do this, okay, we will need to introduce a concept we call finding the characteristic equation. Recurrence relations, you could associate it with a polynomial called characteristic equation. When we get the characteristic equation, we shall get the roots of that characteristic equation. Once we get the roots of the characteristic equation, it will help us to now solve the recurrence relation. We could also call this solving recurrence relations. We can say, this is also, in some textbooks, we will say it as this: solving linear homogeneous recurrence relations of degree 2, because that is what we want, of degree 2. And this means writing the explicit formula, so that once we write the explicit formula, then we don't need to, it's no longer recurrence. Okay, it's just a sequence right away, and we can get any term that we want without having to know the preceding term, the previous terms, or the previous term, as the case may be. Okay, so we write this, the degree 2 goes like this: A subscript n is C times A subscript n minus 1 plus D times A subscript n minus 2. This is degree 2. Okay? Now, our characteristic equation, we call it characteristic equation, would be, this will be x squared equal to C times X plus D. That is our characteristic equation. And you might ask me, how does this work? Well, let me, we are not going to, like, this video, I don't want it to be too long. We will not go into big details, but let me explain something to you. We can write a polynomial to be associated with this recurrence. And if we do that, we can express that polynomial, okay, because this is degree 2, we write x squared equal to the constant times x plus d, just a constant. We skip that one. Let's look at another example. Let's say we have degree 3. Let's say C times A subscript n minus 1 plus D times A subscript n minus 2 plus E times A subscript n minus 3. If you look at this, for instance, this is degree 3. This is degree 3. Okay? Degree 3. So the characteristic equation The characteristic equation in this case would be x cubed, because it's degree 3, we write x cubed, equal to cx squared plus dx plus e. So you see how it works. Okay? So that is the way it works, the characteristic equation. And if we have something like degree 4, a subscript n to be c times a n minus 1 plus d times a n minus 2 plus e times a subscript n minus 3 plus f times a subscript n minus 4. This is a linear. They are all linear. Okay? Remember, it has to be linear, everything we're doing. Okay? The constant times the term, the previous term. So this is a linear homogeneous recurrence relation of degree 4. The characteristic equation would be x to the 4, because it's a degree 4, equal to cx cubed plus dx squared plus ex plus f. That's the way it works. Okay? But like I said, our focus is on degree 2. Okay, but I'm just trying to at least give you an overview of how you write characteristic equations. It is the polynomial we associate with that recurrence relation, and it is used for the purpose of finding an explicit formula for that relation, because the roots of that characteristic equation are very important to us. Very important to us. So we have this as x squared equal to cx plus d. And then we write it as an equation. We have to write it as an equation and then solve the equation. X squared minus cx minus d equal to 0. And then we solve it as an equation to get our roots. Once we get our roots, we will now write a linear system, a 2 by 2 linear system. Okay? And then find another 2 constants, which will now help us to write the explicit formula. Okay? So, we are going to do 3 problems. Okay? By the time we do the first problem, second problem, third problem, you will understand it. Okay? You will understand it. Okay? By the grace of God, you will understand it. Okay, so let's just do examples and then we move from there. Okay, let's do examples and then we move from there. So, our first example will be, let's just say, the Fibonacci sequence as our first example. Okay, I know it might take us some time to do, but that's fine. But let's do the Fibonacci sequence first. At least most of you now are aware of Fibonacci sequence. Okay, you get the term besides the first 2 terms. Okay, each term is got from the preceding term. From the preceding 2 terms. Right? You get each term from the preceding 2 terms. Besides the first 2 terms, you get each term from the preceding 2 terms. Let's look at example 1, Fibonacci sequence. Question 1. Write the explicit formula, okay, for the Fibonacci sequence below. So, with this particular Fibonacci sequence, let's make the initial conditions first term to be 1, second term to be 1. Okay? So, you know, with the Fibonacci sequence, you have 1, then you have 1 again, then 1 plus 1 is 2, then 1 plus 2 is 3, then 2 plus 3 is 5, then 3 plus 5 is 8, then 5 plus 8 is 13. So look at what I'm saying here. Look at what I'm saying. Let's say Fibonacci sequence. Let's say the sequence is F. Okay. So like F1, initial conditions. Let's say the initial conditions are F1 to be 1 and F2 to be 1. So let's call the F the nth term of the Fibonacci sequence. First term is 1, second term is 1. So we see here that the third term is F1 plus F2, F subscript 1 plus F subscript 2, and that is 1 plus 1, which is 2. That is the third term. Third term. Okay? And if you want me to kind of write it, if you want me to write it here, space it out, I will. 1 plus 2, 3, 2 plus 3, 5, 5 plus 3, 8. So this here, I'm using yellow chalk. This is the first term, second term, third term, fourth term, fifth term, sixth term. Okay. The fourth term would be F2 plus F3, the second term plus the third term. Okay? Actually, let me write it as F3 plus F2, which is now 2 plus 1, and that is 3. So the fourth term is 3. The fifth term will be the fourth term plus the third term, and that will give us 3 plus 2, and that is 5. So we could say from here, you could have that the nth term, F subscript n, is equal to the previous term n minus 1 plus n minus 2. Okay, this is the recurrence relation. As you can see here, this is a linear, as you can see here, this is the linear recurrence relation. Linear homogeneous recurrence relation. Degree 2. Okay? Actually, if you want, you can say the third term to be the second plus the first, since we do it that way. Okay? 3 minus 1 is 2. 3 minus 2 is 1. 4 minus 1, F4. 4 minus 1 is 3. And 4 minus 2 is 2. Fifth term, 5 minus 1 is 4. That means the fourth term. Plus 5 minus 2 is 3. Okay? The third term. So, as you can see here, the Fibonacci sequence, okay, where each term in the sequence, besides the first two terms, each term is got from two preceding terms, two previous terms, preceding. Okay? Each term, besides the first two terms, each term in the sequence is got from the two preceding terms. Okay? Third term is got from second term and first term. Fourth term is got from third term and second term. So now, and this has a lot of applications anyway, but that is not our concern. Our concern right now is, how can we find like the 12th term of this sequence? And we don't want to, first of all, find the 10th and 11th term. We don't want to do that before we find the 12th term. No. The purpose will be defeated. We want to find 12th term directly. Period. We want to find the 12th term immediately. So this is a recurrence relation, degree 2. How can we now write the explicit formula for that? That is what we want to do in this video. Okay, so let's start. Let's get started. Okay, so we see that the nth term is the previous term plus the term before the previous term. Okay? So this means 1 times the previous term, because that is our constants. Okay? Plus 1 times the term before the previous term. So if we compare it to this, we could see now that our C is 1 and our D is 1. Okay? Now, we were also given initial conditions. Okay? Given initial conditions. We were given initial conditions. And what were the initial conditions? That F1 is 1, the first term is 1, and the second term is 1. Okay? Now you were not given this. You were given, let's say you were given just this. You were given this, the sequence, the recurrence sequence, and the initial conditions. You have to find the rest. So, first of all, we have written our constants, C and D. Okay? Now the next thing we have to do is to write the characteristic equation. So let's write the characteristic equation. Characteristic equation from this here, from this sequence, we see that x squared is equal to c times x plus d. Okay? Our c is 1 and our d is 1. Remember, when we compared it to that, the constants. So from here, x squared is equal to x plus 1. X squared is equal to x plus 1. Okay? Now, let's solve for the roots of this equation. So we have x squared minus x minus 1 is equal to 0. Can we factor this? Negative 1 times x squared is negative x squared. And the discriminant, b squared minus 4ac. Yeah, negative x squared, negative 1x squared. We cannot factor this. We cannot. So let's use quadratic formula. Let us use quadratic formula to solve it. So I see that here a is 1, b is negative 1, and c is negative 1. With the quadratic formula, we have that x is minus b plus or minus square root of b squared minus 4ac all over 2a. Okay? So x will be minus 1 plus or minus square root of minus 1 all squared minus 4 times 1 times minus 1 all over 2 times 1. Right? So we come over here, x will be minus 1 is 1, plus or minus square root of minus 1 all squared is 1, minus 4 times 1 times minus 4, this is minus 4, all over 2 times 1 is 2. So x will be 1 plus or minus square root of 1 plus 4 all over 2. X will now be 1 plus or minus square root of 5 over 2. Now, let's get the roots of the equation. So the roots of the equation, of the characteristic equation, very important to us. We need the roots, very important. x1 is 1 plus square root of 5 over 2, okay? And then x2, x2 will be 1 minus square root of 5 over 2. These are roots, very important, we need them, okay? Now, I'm going to write the roots here again. I'll write it here again. Let me go ahead and erase this. You already know question 1 that we are working on. So let me write the roots here. x1 is 1 plus square root of 5 over 2, and then x2 is 1 minus square root of 5 over 2. All right. Okay? The next thing we are going to do now is we are going to get the two constants. Okay, we had we're going to get the two initial conditions. I'm sorry, not constants. The two initial conditions. And we will have constants again that we are going to use these characteristic roots for. Okay? That we're going to use the two characteristic roots for. These are the initial conditions. The first term is 1 and the second term is 1. Okay. So this is what we are going to do. Watch me do it. So F1 would be, we want to introduce two constants again. But now these constants are of the initial conditions, not the constants of the recurrence relation. No, it is not the constants of the recurrence relation. Please, I'm not smiling at you, When I teach, I'm happy. Like, teaching is a talent from God. It's my talent from God. When I teach, I'm happy. So, please, I'm not smiling at you. I'm not laughing at you, I'm not laughing at you. So, we are going to introduce two constant, and please, this is the steps that I'm doing is the way you're going to solve it. And don't worry, we will check it. The nice thing about this is that we will check it and see whether it works. That is the nice thing. We will check it. We will check it. We will check it. So we are going to introduce two constants again. Now, those two constants are the constants of the initial value conditions. And once we get that, then the problem is almost over. Now, those two constants, we're going to get the values of those two constants. Okay? Those two constants, we're introducing them as a linear system. And then we'll solve that linear system. And once we solve that linear system, the values of those constants will give us we're going to use those two values to now write the explicit formula. That's something I just remembered now. We wrote the linear homogeneous recurrence relation. We wrote the formula, right? Please, I want you to put condition there. N is greater than or equal to 0. I want you to put that condition. So I'm going to write it here. N greater than or equal to 0. I just remembered it now. I don't think I put it. So after we define those terms, write it underneath. That N is greater than or equal to 0. Okay? So back to business. We're going to write a linear system. A linear system, and we introduce two constants again. F1, the first initial condition. We say alpha times x1 plus beta times x2. Then this second term will be alpha times x1 squared plus beta times x2 squared. Okay. Where, you write again, where alpha and beta are constants. Associated with the initial conditions. Associated with the two initial conditions. Okay? That alpha and beta is necessary. We need to find those. We need to find the values of alpha and beta. Okay, remember our F1 is 1 and our F2 is 1. So what we're going to do now is we'll solve it. So 1 is equal to alpha times 1 plus root 5 over 2 plus beta times 1 minus root 5 over 2. Okay? And then let me call this equation 1. Equation 1. And then the next one, F2 is 1. 1 is equal to alpha 1 plus root 5 over 2 all squared plus beta times 1 minus root 5 over 2 all squared. I call this equation 2. Okay, I don't like fractions. I don't know about you, but I don't like fractions. I don't. So what I'm going to do, although I can solve fractions, no problem. But ordinarily, do you like fractions? I mean, I don't care about fractions. I don't. But to make it easy for you, because I know some of you see fractions and you say, oh, no. Okay, so let us remove the fractions. Let's remove the fractions. From equation 1, we can see that the LCD, what's the LCD? LCD is 2. So we multiply everybody by 2. Okay, this is equations with fractions. We multiply everybody by 2, so we can remove the fractions. So this is 2 times 1 is equal to 2 times alpha times 1 plus root 5 over 2 plus 2 times beta times 1 minus root 5 over 2. I'm using alpha and beta, okay? I have used a lot of English ones, C, D, E, F, X1, X2. I don't want to confuse you again. So let's use alpha and beta. Alpha and beta. These are Greek alphabets. Alright, so 2 is equal to, bam, bam, 2 divided 2, that's gone. So this is alpha times 1 plus root 5 plus, bam, bam, beta times 1 minus root 5. Okay? So I can now say that alpha times 1 plus root 5 plus beta times 1 minus root 5 equal to 2. Let me call this equation 3. Equation 3. I call it equation 3. So I will erase this. So I have alpha times 1 plus root 5 plus beta times 1 minus root 5 equal to 2. Equation 3. Okay? From equation 2, we could remove the fractions as well. So from equation 2, our LCD will be 4, because you see that this is squared, okay? Because this means 1 equal to alpha 1 plus root 5 all squared over 4 plus beta times 1 minus root 5 all squared over 4. Okay? So, LCD is 4. So this multiply everybody by 4. 4 times 1 is equal to 4 times alpha times 1 plus root 5 all squared over 4 plus 4 times beta times 1 minus root 5 all squared over 4. Okay? So 4 times 1 is 4 equal to alpha 1 plus root 5 all squared plus beta 1 minus root 5 all squared. Right? Okay, so we come here, we write alpha 1 plus root 5 all squared plus beta 1 minus root 5 all squared equal to 4. Let's call this equation 3. Equation 4. Let's call it equation 4. Alright, folks. How do we find alpha and beta? We need to find that. And, whenever I have a linear system and I know matrices, I just use Cramer's rule. It's much easier for me doing this kind of question. Doing this kind of question, to me, is much more easier for me to use Cramer's rule right away. It's much more easier for me. So I will set this up as matrices. I have 1 plus root 5, 1 plus root 5 all squared. So if you don't know Cramer's rule, if you want to understand what I'm doing now, then you need to view the videos I did on matrices and determinants. Solution of linear systems using Cramer's rule. Okay, Cramer's rule is also known as the method of determinants. It's easier for me that way. Now you can solve it any other method you like. But for me, I'll prefer to use Cramer's rule. So I have this, and I have 1 minus root 5 here, 1 minus root 5, then here 1 minus root 5 all squared. Okay? Then alpha, beta equal to 2, 4. 2, 4. Okay? Alright, so what's my alpha? Alpha will be determinant 2, 4, 1 minus root 5, 1 minus root 5 all squared, all over determinant 1 plus root 5 by column 1 plus root 5 all squared, 1 minus root 5, 1 minus root 5 all squared. This is my alpha. And my beta will be determinant 1 plus root 5, I'm doing it by column, 1 plus root 5 all squared, then 2, 4, all over determinant 1 plus root 5, 1 plus root 5 all squared, 1 minus root 5, 1 minus root 5 all squared. I close the determinant. The nice thing about Cramer's rule is that you could do it by determinants. Okay, you can do it by determinants. Okay? You could do it by determinants. Like the denominator is the same. That is the nice thing about Cramer's rule. So I will prefer first of all to get the denominator because it's the same. So let me get that determinant, the denominator. I prefer to do that first. Alright, before I now find the numerators. Okay. So we're still here. Yeah, that is the thing about a Fibonacci sequence. Now, not every sequence is like this. Okay? This is just if we factored out the characteristic equation, if we could solve that characteristic equation by factoring, then this wouldn't be like we wouldn't be doing a lot of things now. If we could have factored it by factoring, if we could have solved it by factoring the characteristic equation, it would have been a lot better. Okay. But no problem. We are equal to the task, right? We like challenges, right? Okay, alright. So let's start with the denominator. 1 plus root 5. 1 plus root 5 all squared. 1 minus root 5. 1 minus root 5 all squared. What is the determinant? I'm going to use the shortcut. I'll use the shortcut. So this gives us 1 plus root 5 times 1 minus root 5 all squared minus 1 plus root 5 all squared times 1 minus root 5. Okay? Alright? So this will give us, let me put brackets in this, okay? So I have 1 plus root 5 times 1 minus root 5 times 1 minus root 5, I close the bracket, minus 1 plus root 5 times 1 plus root 5 times 1 minus root 5. Okay? So this will give me 1 plus root 5 times 1 minus root 5. Difference of two squares is much better. I want to do it that way. It's much better for me. So this is 1 squared minus root 5 all squared. Okay? This right here. this right here. This right here is this. Okay? Then times 1 minus root 5. Then minus 1 plus root 5 times 1 squared minus root 5 all squared. So this right here, I'm using a yellow chalk. This is this. If you want to foil it, that's fine. If you want to foil it. But I don't want to foil it. I mean, because I could use difference of two squares, which is easier for me. Okay? Which is much easier for me. Let me put this parenthesis as well. Difference of two squares is much more easier for me. Alright, so this will give me, this is going to give me 1 squared is 1 minus root 5 all squared is 5. So 1 minus 5 times 1 minus root 5 minus 1 plus root 5 times 1 minus 5. Okay? So what we got? We now have 1 minus 5 is minus 4. Minus 4 times 1 minus root 5 minus 1 plus root 5 times minus 4 times minus 4. Okay? Alright, so let's finish this. So what would this give us? What would this give us? We now have that this will be, we distribute that, minus 4 plus 4 root 5, okay? Minus, you know what, let me write it here. Let me write it here. So, hey, I wouldn't have, you know what, I wouldn't have erased this, okay? But I know that this is 2, 4. Alpha is 2, 4, 2, 4, right? Alpha is 2, 4. Yeah, let us not erase alpha and beta. I need it. I really need alpha and beta. So I had 2, 4 here, and I had 1 minus root 5 all squared here. Okay, and then this is still, because I need this. I really need it. This is 1 minus root 5, and then 1 minus root 5 all squared. Okay. Yeah. And then our beta was 1 plus root 5, 1 plus root 5 all squared, then 2, 4. All over this. Okay? 1 plus root 5, 1 plus root 5 all squared, 1 minus root 5, 1 minus root 5 all squared. Yeah, I need this. I really do. Okay, let's finish up this. Let's find the denominator. Okay? I hope that is correct like that. This was this first, then this. Okay. All right, folks. Let's finish up this. So from here, this will be, we distribute that. Okay, if we distribute that, this is negative 4 plus 4 root 5 minus, that is negative 4 minus 4 root 5. Okay? Negative 4 times 1 is negative 4. Negative 4 times plus root 5 is negative 4 root 5. So let's open up the parentheses. This will give us minus 4 plus 4 root 5 minus minus plus 4 minus minus plus 4 root 5. Please don't mind my dog. Okay, don't mind her. So minus 4 plus 4, that's gone. 4 root 5 plus 4 root 5 is 8 root 5. So this is 8 root 5. Okay? So our determinant for the denominator is 8 root 5. So let's write it somewhere. Let's write it somewhere. Let's write it here. That this determinant is 8 root 5. 8 root 5. I will just get it here. Okay? This is 8 root 5. Oh, you know what? Let's now come over here and we just write this 8 root 5. 8 root 5. 8 root 5 and then 8 root 5. Because we need space. We need space. 8 root 5. Okay? Alright? Now, let's solve the numerator for the alpha. Once we get alpha and beta, we are almost done. Trust me, almost done. And then we can now check our work. So don't worry, we're almost done. Let's get the alpha, the numerator for that alpha. So determinant 2, 4, here 1 minus root 5, 1 minus root 5 all squared. Okay? This will give us what? 2 times 1 minus root 5 all squared minus 4 times 1 minus root 5. Okay? So this will give us 2. I'm gonna expand this. 1 minus root 5 times 1 minus root 5. Then minus 4 plus 4 root 5. Right? So this will give us 2. We have 1 minus root 5, 1 minus root 5 minus root 5 minus 2 root 5 plus, minus minus is plus. Root 5 times root 5 is 5. Minus 4 plus 4 root 5. So this will give us 2 times 6 minus 2 root 5 minus 4 plus 4 root 5. Right? So this will give us 2 times 6 is 12. We distribute. 2 times 6 is 12. Minus 2 times 2, 4 root 5. Okay? 12 minus 4 root 5 minus 4 plus 4 root 5. So 12 minus 4 is 8. Minus 4 root 5 plus 4 root 5 is 0. So this is 8. Okay? So our alpha is 8 over 8 root 5. That's our alpha. 8 over 8 root 5. Now let us, which is 1 over root 5. We shall come to that. Okay, no problem. Let's go ahead and do beta, the numerator for beta. Let's do the numerator for beta. If we do that, then we have determinant 1 plus root 5, 1 plus root 5 all squared, then 2, 4 This will give us 4 times 1 plus root 5 minus 2 times 1 plus root 5 all squared. So this will give us 4 plus 4 root 5 minus 2. I have 1 plus root 5 times 1 plus root 5. Okay? And this will give me 4 plus 4 root 5 minus 2, 1 plus 1 root 5 plus 1 root 5, 2 root 5, okay, plus 5. Root 5 times root 5. Root 5 times root 5 is 5. Okay? So this gives me 4 plus 4 root 5 minus 2. 1 plus 5 is 6. 6 plus 2 root 5. So this gives me 4 plus 4 root 5 minus 12 minus 4 root 5. And then I have 4 minus 12 is minus 8. Minus 8. 4 root 5 minus 4 root 5 is gone. So beta will be minus 8, negative 8 over 8 root 5. Okay. Let's simplify that. Let's simplify that. So we now have that alpha is 8 over 8 root 5, right? Which is 1 over root 5. 8 divided 8 is 1. So which is 1 over root 5 times root 5 over root 5. And that is root 5 over 5. So alpha is root 5 over 5. Alpha is root 5 over 5. Beta will give us negative 8 over 8 root 5. So our beta will give us negative root 5 over 5. Okay? Negative root 5 over 5. I mean, you do it the same way. This is negative 1 over root 5, which is negative 1 over root 5 times root 5 over root 5. Okay? Alright, now the next thing we're going to do is this. We can now write our explicit formula. Okay? Almost done, almost done, almost done. So our explicit formula for the Fibonacci sequence, would be the nth term, okay, would be the alpha times x1n. You see, we needed those. We needed alpha, we needed beta, we needed x1, we needed x2. Then plus beta times x2n. That's it. That's our explicit formula. Now, let's finish it. So, the nth term would be alpha is root 5 over 5. Root 5 over 5 times 1 plus root 5 over 2 raised to power n, plus, in this case, beta is minus, plus minus root 5 over 5 times 1 minus root 5 over 2 raised to power n. Okay, let's simplify further. So the n term will be root 5 over 5 times 1 plus root 5 over 2 raised to power n. Plus minus is minus. Minus root 5 over 5 times 1 minus root 5 over 2 raised to power n. Final answer. So our final answer would be that the nth term would be root 5 over, we factor by GCF. Factor by GCF, root 5 over 5 times, let's use a bracket here. Okay, bracket. 1 plus root 5 over 2 raised to power n minus 1 minus root 5 all over 2 raised to power n. And this becomes your answer here. That becomes your answer here. Okay? That becomes your answer. Check it. You want to check it? Let's start with A3. Find A3. Find it. And remember with Fibonacci sequence, this is 1, 1, 1 plus 1, 2, 2 plus 1, 3, 3 plus 2, 5. A3 should give us third term. Okay? A3 should give us 2. Do it. Third term is root 5 over 5. Okay, root 5 over 5, parenthesis, 1 plus root 5 over 2 raised to power 3 minus 1 minus root 5 over 2 raised to power 3. It should give us 2. It should give us 2. Let's try it. I have my calculator. Okay? I know this calculator, I know it somehow. So look at what I'm going to do. Look at what I'm going to do. I'm going to put, this calculator is not too strong for putting it in like that. So I will do this one at a time. I'll do it one at a time. So I will do first of all, 1 plus, well let me put parentheses first. Parentheses, 1 plus, shift square root of 5. Okay, close the parentheses, divided by 2, equal to this. This gives this here, and then I raise it to 3. I raise it to power 3. So this gives me 4.236067977. That's this part here. Okay, I keep it. I'm going to do the next part, parentheses, 1 minus, shift square root of 5. Close parentheses, divided by 2, equal to this. Then raise it to power 3. So this here gives me negative 0.23606797775. Okay, then I now do this minus this. Okay, which minus is plus. So I will do 4.236067977 minus the answer, minus shift answer, because minus will give me plus. So all these here, all this in brackets, gives me 4.4721359554. And then I multiply this times square root of 5, shift square root of 5. It gives me 9.999999999 divided by 5 gives me 2. 2. If you do the fourth term, it will give you 3. You do the fifth term, it will give you 5. Okay? Alright, now, let's solve, by the time we solve 2 more problems, then, you know, it will kind of make more sense, especially when we do number 3 question. So I have some questions here. Question 2. This one is question 2 that we're going to solve now. Question 2. Peter is climbing stairs, taking 1 or 2 steps at a time. You see, this is an application of recurrence. Okay, Peter is climbing stairs, taking 1 or 2 steps at a time. So let this be the number of ways. They say give a recurrence relation for the number of ways Peter can climb n steps. N steps. Okay, that's number 1. B, that's A. Peter, the question is, Peter is climbing stairs, taking 1 or 2 steps at a time. Okay, climbing steps, taking 1 or 2 steps at a time. A, give the recurrence relation for the number of ways that Peter can climb n steps. B, how many ways can Peter climb 12 steps? How many ways can Peter climb 12 steps? So Peter can climb stairs. Peter can climb stairs, taking either 1 or 2 steps at a time. Okay, taking 1 or 2 steps at a time. A, give a recurrence relation for the number of ways that Peter can climb n steps. B, how many ways can Peter climb 12 steps? All right. This is recurrence relation. So let's solve it. Question 2. We've called it out. So in this case, Peter can climb 1 or 2 steps at a time. Okay, he can climb 1 or 2 steps at a time. He can climb stairs either 1 step or 2 steps at a time. So this means the recurrence relation. Okay, let's recurrence relation. Let recurrence relation be climbing. Let's call this. Let's call it T. Okay. Stairs. Let's call it T. Let's call it T. T. So T. Now did I write A to the N? Please, I think I wrote A to the N. That should be F to the N, please. The question I just erased now. It shouldn't be A to the N, it's F to the N. Because we were using F to the N all along. Okay? I don't know why I wrote A to the N. My bad. It's F to the N. So here, let the recurrence relation for our question 2 be T. Okay? Yeah. Please don't be confused, okay? If I wrote A to the N, it should be F to the N. Please. Uppercase F to the N. Because that was Fibonacci sequence. Okay, please. Alright, in this case, let's our recurrence relation for question 2 be T. So T to the N, as we can see, Peter can climb 1 or 2 stairs at a time. So this is our recurrence relation here. Where the initial conditions are T1 can be 1 step, and then T2 can be 2 steps at a time. Can climb 1 or 2 stairs at a time. Okay? These are recurrence relation for that. Peter can climb either 1 or 2 steps at a time. Climbing stairs can do 1 step or 2 steps at a time. So initial condition is 1, the first term is 1, or And that's why we have plus. Plus, okay? Two steps at a time, 2. These 2, we can say it, we can put it as 1 plus 1. Okay? So we have something like this. We have 1, we have 2, which is 1 plus 1. Okay? We have 2 plus 1, which is 3. We have 2 plus 3, which is 5. We have 3 plus 5, which is 8. So this is similar to Fibonacci sequence. It's just that in this case, our T1 is 1 and our T2 is 2 rather than 1. Okay, but this here is still similar to our Fibonacci sequence. So the only thing that changed here are the initial conditions. Those are the only things that changed. Okay, so our characteristic equation is still the same. Our characteristic equation is still the same. Okay, x squared is 1, because this is 1 times c plus d. Okay, 1 times x plus 1. Okay, in this case we have this to be t of n to be 1 times t subscript n minus 1 plus 1 times t subscript n minus 2. So our characteristic equation is still the same thing. But if we compare it, our c is 1 and our d is 1. Okay, so it's still the same thing, just like we did. The only thing that changed here is the initial conditions. That Peter can take 1 step or 2 steps at a time. So the first one is 1 and the second term is 2. Okay? And so what we could do, the next thing we can now do, we find, so our characteristic equation is the same thing. X squared is x plus 1. So x squared minus x minus 1 will give us 0. So our roots, the roots of the characteristic equation is the same thing. The roots are the same thing. The only thing that changed are the initial conditions. So we could now write that. We could write that we could now write T1 will be alpha x1 plus beta x2. And our T2 will be alpha x1 squared plus beta x2 squared. Okay? Because we don't have to, this video is getting too long. So we don't have to come and start, our characteristic equation is the same. So the roots are still valid. The roots are still valid. It's just that in this case, our T1 is 1 and our T2 is 2. That is the only thing in this case here. The only thing in this case. Okay. So, now, the question even says the recurrence relation. This is the answer here. This is the recurrence relation, and you have to put the initial conditions. That's A part. Then it now says 12. How many ways can Peter climb 12 steps? 12 steps. If we want to save time, we could keep doing this until we get to the 12th. We can do that. Actually, if we do that, the B part. How many ways can Peter climb 12 steps? So this is 1. T1 is 1. T2 is 1 plus 1, which is 2. T3 is 2 plus 1, which is 3. T4 is 3 plus 2, which is 5. T5 is 5 plus 3, which is 8. Okay. T6 is 8 plus 5, which is 13. T7 is 13 plus 8, which is 20. 13 plus 8. Which is 21. 21. Okay. T8 is 21 plus 13, which is 1 plus 3 is 4, 3 plus 2 plus 1 is 3, 34. T9 is 34 plus 21, which is 55. Okay. T10, 10th term is 55 plus 34, which is 89. Okay. T11 is 89 plus 55, which is 9 plus 5 is 14, carry 1, 1 plus 8, 9 plus 5, 14, 144. Okay? T12, 12 steps is 144 plus 89. 9 plus 4 is 13, 1. 1 plus 4, 5 plus 8, 13. 1 plus 1, 2, 233. 233 ways. So this is the answer here, 233 ways. Here. Okay? I mean, we could do it this way. We could do it this way. But what if they say, how many ways can Peter climb 25 steps? Would you keep doing it recursively? Would you? Would you keep doing it recursively? Our answer here is 233 ways. Let me write it here. 233 ways. So would you keep doing this recursively? No. No. So now let's just finish this again. You know, as you do, if you want to really understand it, you do problems. Keep doing problems, then you understand it. Okay. So let's go ahead and do this again and get our alpha and beta. Our alpha and beta, very important. What we are going to have in this case would be alpha, let me just write it the other way around, okay? This means alpha x1 plus beta x2 is T1. Alpha x1 squared plus beta x2 squared is T2. Okay, so this will be alpha 1 plus root 5 over 2 plus beta 1 minus root 5 over 2 is 1. Okay? And then alpha 1 plus root 5 over 2 all squared plus beta 1 minus root 5 over 2 all squared is 2. Okay. So The same thing, similar to the question 1. The only thing that changes now is the equation 2. Okay. So from equation 1, from what we wrote in equation 1, this gives us that alpha times 1 plus root 5 plus beta times 1 minus root 5 is equal to 2. Okay? In this case, this will be alpha 1 plus root 5 all squared plus beta 1 minus root 5 all squared. This is now 4. 4 times 2. Because the other one we did was 4 times 1, which is 4. Here is 4 times 2. 4 times 2, and that is 8. 8. Okay? And then we set it up. Let's say I like setting it up as a matrix. So I have 1 plus root 5, 1 plus root 5 all squared. Then I have 1 minus root 5, 1 minus root 5 all squared. And I have alpha, beta equal to 2 and 8. So actually, if we had all those things we did initially, we just, anywhere we see 4, we put 8. Okay, but that's fine. We already know this as 8 root 5. Okay, so it wouldn't be a lot of work anymore. Let's go ahead and finish it. We can do it. We can do it. We do it and then we check it. We check it to make sure it works. Okay? Alpha will be determinant 2, 8, 1 minus root 5 over, 1 minus root 5 all squared, all over determinant 1 plus root 5, 1 plus root 5 all squared, 1 minus root 5, 1 minus root 5 all squared. Right? And our beta will be determinant 1 plus root 5, 1 plus root 5 all squared, then 2, 8. Rather than 2, 4, this is 2, 8. All over 1 plus root 5, 1 plus root 5 all squared, 1 minus root 5, 1 minus root 5 all squared. Okay? Alright, folks. We already know the denominator. Our denominator, we already know is 8 root 5. We already know that. So we shall be concerned with our numerator. Okay, determinant of 2, 8, 1 minus root 5, 1 minus root 5 all squared. This will give us 2 times 1 minus root 5 all squared minus 8 times 1 minus root 5. Right? So this gives us 2. This is 1 minus root 5, 1 minus 2 root 5 plus 5. So 1 plus 5, 6. Right? So 6 minus root 5. That was what we got, right? 6 minus 2 root 5. Remember, we did this already. Okay? 6 minus 2 root 5. Right? Okay? Minus 8 plus 8 root 5. So this will give us 12 minus 4 root 5. 12 minus 4 root 5 minus 8 plus 8 root 5. 12 minus 8 is 4. Okay? 4 minus 4 root 5 plus 8 root 5 is plus 4 root 5. Okay? And that gives us 4 with factor out. 1 factor by GCF. 4 into 1 plus root 5. Alright? So our alpha would be 4 into 1 plus root 5 all over 8 root 5. These are alpha here. Our alpha. Okay? Now let's find our beta. Let's find our beta. Our beta would be we have determined the numerator. Okay. 1 plus root 5, 1 plus root 5 all squared. And then we have 2 8s. So this will give us 8 times 1 plus root 5 minus 2 times 1 plus root 5 all squared. So this gives us 8 plus 8 root 5 minus 2, 1 plus root 5 plus root 5 plus 2 root 5 plus 5. So 6 plus 2 root 5. Right? 6 plus 2 root 5. Okay? So this will give us 8 plus 8 root 5 minus 12 minus 4 root 5. And we have 8 minus 12 is minus 4. 8 root 5 minus 4 root 5 is minus 4 root 5. And that gives us minus 4 factor by GCF minus 4 1 plus root 5. Okay? Minus 4 1 plus root 5. So I'll come over here. I'll write this. So this will be minus 4 parentheses 1 plus root 5. And this is all over 8 root 5. Okay. We are going to rationalize this. Let us simplify it. We cannot leave it like this, no. We have to simplify it. Okay? Now 4 into 4 is 1. 4 into 8 is 2. And then here 4 into 4 is 1. 4 into 8 is 2. Okay, let's rationalize. So our alpha will be 1 plus root 5 all over 2 root 5. We don't have to leave it this way. This is what we got as our alpha. But let us rationalize it. Let us rationalize it. This is times root 5 all over root 5. So this will give us root 5 times 1 plus root 5 all over 2 times 5. Right? Root 5 times root 5 is 5. So this will give us root 5 times 1 plus root 5 all over 10. These are alpha. And our beta is going to be minus, just the minus of it, the opposite of the alpha. Okay? Minus root 5, 1 plus root 5 all over 10. This is our beta. Okay? So we're almost done, bro. We're almost done. So now our n term is alpha times x1 raised to power n plus beta times x2 raised to power n. So our n term will be root 5 times 1 plus root 5 all over 10 times 1 plus root 5 over 2 exponent n plus, well, plus, beta is minus, plus minus is minus, minus root 5 times 1 plus root 5 all over 10 times 1 minus root 5 over 2 exponent n. Right? Okay, let us factor by GCF. So our n term will now be root 5 times 1 plus root 5 all over 10. Then 1 plus root 5 over 2 exponent n minus 1 minus root 5 over 2 exponent n. This is our explicit formula. Okay, folks, let us check first. Let us check it. Okay, let's check and see whether it works. So the 12th term, T12, 12th term, this will be root 5 times 1 plus root 5 all over 10 and times 1 plus root 5 over 2 exponent 12 minus 1 minus root 5 over 2 exponent 12. Okay? So this will be, let's check this. We will do it with, let's check it with my simple calculator. Let me do this one first. Parenthesis 1 plus shift square root of 5 divided by 10 gives me this. Then times root 5, shift root 5. Okay, this gives me 0.72360 okay, times parenthesis 1 plus shift root 5 divided by 2 then raised to power 12. This gives me 321.9968944 minus parenthesis 1 minus shift root 5 divided by 2. This is a negative number, but exponent 12 gives us a positive number. This is 0.00310.562.0015. That's kind of big. All right, so let's go ahead and I'm going to subtract this and then I multiply it. So 0.7236067977 times 321.9968944 minus shift answer. So this gives me 321.993.7888. Okay, times 0.7236067977 gives me 232.9968944. And come on, folks. It's approximately 233 ways. Okay? I mean, if you just put it in without rounding, because this is even rounded, otherwise it will give you 233. Alright? Same way, same thing. With this, you can do 25 steps. How many ways can Peter climb 25 steps? How many ways can Peter climb 100 steps? You can do it with explicit formula. Okay, last but not the least, question 3. Question 3, we have let the recurrence relation a to the n be minus 4a subscript n minus 1 plus 21 subscript a n minus 2. Okay. It says, write the first, so this question has ABC. A, write the first 5 terms of the recurrence relation. Write the first 5 terms of the recurrence relation. B, solve the recurrence relation. Solve the recurrence relation. C, using the explicit formula you found in part B, evaluate A subscript 5. Okay? Using the explicit formula you found in part B, evaluate the 5th term. Evaluate A to the 5th. Evaluate A to the 5th. Okay? And it says you must show that you are using the equation from part B. Okay? No problem. I got you. I got you, no problem. Okay, folks, let us solve this. What will be our C and what will be our D? Okay, in this case, remember from what we wrote in the first equation, A(n) is C times A n minus 1 plus D times A n minus 2, right? So if we compare this and this, compare, our C is minus 4, our D is 21. If we compare. Okay, now what is our characteristic equation? Let us find our characteristic equation. Wait a minute. Before we do this, let's solve the A part. I'm sorry. Let's solve the A part. A. Write the first 5 terms of the recurrence relation. So the recurrence relation is A equal to minus 4 times A n minus 1 subscript n minus 1 plus 21 times A subscript n minus 2. Okay? And then they gave us, let's see, okay, they gave us the initial conditions. That was what I was looking for. A1 is 106. They gave us the initial conditions. A1 is 106, initial conditions. And A2 is negative 382. Negative 382. Okay. So, of course, we have our A1, 106. Okay. A2 is negative 382. This was given. A3 would be minus 4 times A3 minus 1 plus 21 times A3 minus 2. So this means minus 4 times A2 plus 21 times A1. Do you see that? Do you see what I'm doing? Recurrence. So this will give us minus 4 times, I am showing all my work, okay? Minus 4 times minus 382 plus 21 times 106. And that gives us what? Minus times minus is plus. 4 times 382. This is 1528 plus 21 times 106. 2226. So our A3, 2226 plus 1528. 3754. Okay? That's our A3. You know what? I'm going to write it here. I'm going to write it here. So our A3 is 3754. Alright. Our A4 will be minus 4 times A 4 minus 1 plus 21 times A 4 minus 2. Okay? Which is minus 4 times A3 plus 21 times A2. Right? Which is minus 4 times 3754 plus 21 times minus 382, which will give us minus 4 times 3754 is 15016. Plus times minus is minus. Minus 21 times 382. Okay? Will give us 8022. 8022. So you owe minus 8022 plus 15016. So minus 23038. So A4, and you can verify this. Verify it on your own. So A4 is minus 23038. Okay? Now let's do A5. A5. Okay. So the first 5 terms, of course, we have our A1 is 106, A2 is minus 382. So A5 is the next one we need to find. Okay. A5 would be, our A5 would be minus 4 times A 5 minus 1 subscript plus 21 times A subscript 5 minus 2. So that will give us minus 4 times A4 plus 21 times A3. Okay? Which is minus 4 times A4 is minus 23038 plus 21 times A3 is 3754. Okay? We'll get a big number. Big number. So our A5 would be minus times minus is plus 4 times 23038. That is 92152 plus 21 times 3754 is 78834. So the fifth term would be this plus 92152. 170986. This is the fifth term. 170986. All right. We found the A part. We found it. The first 5 terms of the recurrence relation. Now, let us solve the recurrence relation. Solving it means finding an explicit formula for it. So we solve it. If we write this in that order, in that initial way that I wrote it, an to be c times a n minus 1 plus b times a n minus 2. Okay, this is a linear homogeneous recurrence relation of degree 2. Okay, remember this video is for degree 2, part 1 of this video. That's part 1 is this video. So if we compare this, our c is minus 4 and our d is 21. If we compare this, it. Now, what is our characteristic equation? Remember, our characteristic equation, we say it was x squared equal to cx plus d. That was what we said, okay, when we did this. So, put it back here. In this case, our x squared is equal to negative 4x plus 21. Right? Negative 4x plus 21. So, our x squared plus 4x minus 21 equal to 0. Minus 21 times x squared minus 21x squared. 1 and minus 21 will not work. Minus 1 and 21 will not work. 2 will not work. 3 and minus 7 will not work. Minus 3 and 7. Minus 3 and 7 will work. So this is x minus 3, x plus 7, okay, equal to 0. Good. So our x minus 3 is 0, so x is 3, or x plus 7 is 0, x is minus 7. Okay, we just solved this by factoring. Alright, so our x1 is 3, and our x2 is minus 7. Let's keep that. Okay? We now set up a linear system with the initial conditions. We set up a linear system. A1 is equal to alpha times x1 plus beta times x2. A2 would be alpha times x1 squared plus beta times x2 all squared. Okay? So if we do that, what we're gonna get? We will see that A1 is 106 is equal to alpha times 3 plus beta times minus 7. Okay? And then minus 382 will give us alpha times 3 squared plus beta times -7 all squared. Okay, the same step we've been doing. The same step. The same thing we've been doing. Same step we've been doing. Okay, I will need space. I will need space. So I'm going to erase this, but I will leave this here. Okay, at least you guys, the B part means we will find the explicit formula. And then we will now just we'll use the explicit formula and find the 5th term and see whether we will get the same thing. Okay, so, but I will need space. So I will erase this here so we can finish up this. So from here, let's rearrange it well. We have that 3 alpha minus 7 beta will give us 106. Let's call this equation 1. Okay? And then equation 2, 3 squared is 9. 9 alpha minus 7 all squared will give us 49. So this is plus. Plus 49 beta will give us minus 382. 382. Okay? Call this equation 2. Now let's find our alpha and beta. I would like doing it Cramer's rule right away. So I'll put this in matrix form. We have 3, 9, minus 7, 49. Alpha, beta equal to 106 minus 382. Okay? Cramer's rule saves a lot of time. And I will leave this main recurrence and then I will erase this so we can finish this. So our alpha would be determinant 106 minus 382 minus 749 all over determinant 39 minus 749. And our beta will be determinant 39 106 minus 382 all over determinant 39 minus 749. Okay? Alright. Now let's find our alpha. So our alpha would be 106 times 49 minus plus, well, minus, okay, this times this, minus 382 times minus 7 all over this times this minus this times this. 3 times 49, okay, minus 9 times minus 7. Alright? So, our alpha, I hope we know our roots, x1 and x2. Our x1 was what? And our x2 was what? Hey, we need that. Our x1 was, our x1 was 3 and our x2 was -7. Okay, I'm going to write it here because I need it. x1, x2 is 3 and -7. Okay? Very important. We did it in the last part of the quiz. Okay, so our alpha would be 106 times 49 is 5194 minus times minus is plus 382 times 7 2674 all over 3 times 49 is 147 minus times minus plus 63. So we have 5194 minus 2674 is 2520 all over 147 plus 63 is 210. So 2520 divided by 210 is 12. Okay, our alpha is 12. We keep that, we need it. And our beta will just be 3 times negative 382 minus 9 times 106 all over 210. That is the nice thing about Cramer's rule. The nice thing. The denominators are the same. The denominators are the same. So our beta would be 3 times 382. So we have minus 1146 minus 9 times 106 minus 954 all over 210. And that gives us minus 1146 plus 954 minus 2100 all over 210. So beta is minus 10. Okay, we need this. Okay? Now folks, we are almost done with the explicit formula. So if we write the explicit formula, we will have that almost done. Almost done. You see how Cramer's rule is pretty much fast. So our explicit formula is a subscript n will give us alpha times x1 exponent n plus beta times x2 exponent n. Okay? So a subscript n will give us 12 times our x1 is 3 exponent n plus beta is minus 10 times minus 7 exponent n. So the final answer would be, if we simplify this, this will be 12 times 3 exponent n minus 10 times minus 7 exponent n. So this is our recurrence relation here. So this is our explicit formula for the recurrence relation. Okay? Let us now, the last question says, using the explicit formula you found in part B, evaluate the fifth term, A subscript 5. You must show that you are using the equation from part B. And we have to get the same thing. If we don't get the same thing, we're in trouble. Okay? If we don't get the same thing, we have to do it again. We have to do it all over again. We've got to get the same thing. Even the part 2, you know, we got 232.9 something. If we didn't round, if there was no rounding, it will give us exactly 233. It will. Okay, so let's do part C of this. Let's do part C of this. here. So the C part, n equal to 5, so A5 would be 12 times 3 exponent 5 minus 10 times negative 7 exponent 5. And that gives us 12 times 3 exponent 5 is 243 minus 10 times negative 7. Negative 7 exponent 5. That should give us a negative number. Minus 16807. Okay? Negative base to odd exponent will give us a negative result. Negative base to an odd exponent. If the base is negative, exponent is odd, it will give us a negative result. Okay, so this is 12 times 243 is 2916. Minus times minus is plus. Plus 168070. Okay? Plus 168070. And that gives us 170986. Yay! 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 So we can jump up and touch the ceiling because we got it right. Okay? Or we can drink water. Not soda, no. Soda gives you big tummy. Not soda, not alcohol, but water. Okay? Yeah. Okay, folks, we shall stop here for tonight. If you have any questions, please feel free to ask me. Remember, if you are my student, please do not contact me from my website. If you're my student, do not ask questions on YouTube. No, ask questions in the school system. Okay, I don't check my YouTube, I don't check YouTube comments all the time. It's when I have time to check them. So if you have any questions, if you are my student, go ahead from the school system. If you're not my student, you can contact me from my website. Thank you so much for